Alright, we are going to be doing after binomial distribution question, the hypergeometric distribution. So for hypergeometric distribution, you have to remember a couple of things. First of all, we have the total population pool of n. But first of all, you should also know that this is also we have this familiar concept in binomial distribution. The reason why we use hypergeometric is because for binomial, we had the concept and the background which was with replacement. Whereas for hypergeometric, it's going to be without replacement. Now, how shall I explain to you? This would be better explained with the help of an example. So you draw green balls from a total population of, let's say, 7 balls you have 7 balls, and out of that you have 3 greens, right? And you can have 4 red. Or it could be the other way around. It could be 4 green and 3 red balls. That's it. Now, if I draw balls and then just replace them back and then draw them, so that could be, giving us some results with a certain trend of successes and failures. So we can have, let's say, out of n number of experiments that we do, so that would be the small. This is n is the number of drawings that we actually have, the number of drawings. And right now, the main difference is that we are, first of all, considering that it's going to be with replacement because we are putting back the balls, then selecting them, then putting them back, and then making another selection. So we have n number of iterations in this case. Iteration means that you're having repetitive experiments in this case. So now you have n number of drawings. That means that out of the 7, you can have 5 drawings, right? You can have 5 drawings. That means you can draw 5 balls at one time, and you could also repeat this experiment with cards or with anything. I could be repeating with number of students in the class, and I could be picking them, putting them back for a certain behavior trend. I want to see how many of them have exam anxiety, for instance. And now in this COVID situation, I'm sure many of you have overcome that anxiety problem. However, when we're talking about the regular examination scenario where you can have people, turning in their exam, and let's say for the very fact that the very question they left, that same question came in the exam, so that would be exam anxiety in this case. So how many students we can have any number of drawings, and we can have any number of situations in this case. So out of those 5 drawings now, if I, take out a ball, the probability that is going to be my favorite color, let's suppose I say that it's green, is going to be 1, 2, 3, 4, so there could be 1 green, 2 green. So if I'm making 5 drawings, so then you can have X as the success. And the pool of n is going to be equal to 7, and the number of drawings is going to be equal to 5. And we have success as X. But for binomial distribution, usually we have probability of R by n in terms of probability, which is raised to power X, right? Because we are having this as the number of successes that we can have as X. So, but I'm not talking about the factorial right now, I'm just talking about the probability of success. Naturally, we have it raised to the power of whatever the percentage was into 1 minus p. If you recall, we did the failure part where we had 1 minus anything, which is the success. In complement to that, you revisit the complement concept in this case, so we can have n minus x, because now x has been removed from the selection of 5. So drawings of 5, and in this case, so we have 5 minus successes, and these could be 3, let's suppose, or 2, or 1, whatever that we have. If we want green, so that would be x equal to. Now that is going to be 0, 1, 2, 3, and so on and so forth. However, when we don't replace the balls, right? If I don't replace the ball and I, take out the ball and I just keep it aside, now then these experiments could be limited, right? But for hypergeometric distribution, usually the number of experiments they have to be very large, and the population also can be very large, and it can approximate to binomial. If n becomes larger than, you know, a certain level, let's say it could be larger than 20 or 30 or 40. So we have to fix a number, but usually it's 20. And that's reasonable. We can have 20 responses or 30 responses, but a pool of, now what could be 20 actually? That is what matters. If we have a number of repetitions very large, out of those, that populace of 20, let's say, we can have a number of iterations or repetitions of an experiment of 1,000 times. Now within that 1,000, it would mean that if you have, like I gave you an example a while ago, that it was, you know, dust specks on a piece of cloth. So now you can know if we're talking about a whole blotch, then that is countable. But if we have, you know, let's say something which is a small speck, it's a grain of sand, let's say. So how many grains of sand can actually exist? Or how many dust specks can, or dust particles could exist? So if you study the molecular structure, then that will be going very deep into it. So we can have a number of, X possibilities could be very large in this case, and factorial in this case, because we have to consider the combination. So factorial could be very large. So it is always better than to approximate it to binomial in this case if it becomes large. Otherwise, you can have this, you know, calculated as, for failure is going to be 1 over, and then we can have n minus 1, as this could be something which could have a bias. So we can always have that bias-free result. All right. So then that could be, basically, it's all, right now, I would just keep it as n just to simplify this, okay? Usually we simplify both p and q with having the same denominator. But for hypergeometric distribution, that is not all. For binomial, we had p and q. Now we have to consider the whole formula by keeping r as a factor of success in this case, because x could be the this could be, r is the potential success. Now what is potential success? So basically I said that n items, and r of these items, let's say r of these items are successes, potential successes. So that means that failures could be, n minus r, right? Because x is something that we will study, whether out of those successes, what is the given value, whether the probability out of it, of that success is whether it could be 0 or 1 or 2 or 3, and I'm just going to be explaining the difference to you in a while, but that could be the potential success, r in this case. Now sometimes I say potential success could be if I have the number of balls in this case as 4. Can I have out of the 5 drawings the potential success of x equal to the probability that x is equal to 0? Can it be that x is equal to 0 if I have 5 drawings, and out of those 5 drawings I have green with 4 and red as 3? The answer is no, we cannot have that. Why? Because the number of drawings are 5 and it is exceeding the number of balls that the other color can actually be, color that other ball can have. So if this is the red colored balls are actually 3 in quantity, that means in my 5 drawings I could have 2 green and 3 red. So the probability that x is 0 or x is 1 even in this case is impossible. So it's going to be 0. That means, okay. So that would be, so you have to be reading the question first and then considering that out of these potential successes, what is the probability of a particular success being 0, 1, 2. So out of these successes, probability that x could be 0 is 0. Now you understand the difference, I hope. And then again, the failures could be n minus r. So in a formula, if I just, turn this around in a formula. So I can have a combination of R successes total with what I desire X, right? This could be also sort of like we make selections, and out of those selections we can have R successes. And then, now N is the total population, like I said, minus. Now I'm talking about failure in the same way that I was speaking about failure for binomial distribution, but only now N has to be having number of iterations with the values that could be very large, all right, and where one single outcome is so insignificant that it cannot have an impact on overall value of N. So in that case, then we would be approximating it to binomial distribution, and now I can subtract R from it, and N is the number of selections or drawings that I made, and out of that N I can have for failure N minus X, because naturally if I make selection of 5 drawings, let's say, and out of that 4 is green, then naturally 3 will be red. So out of 7, let's suppose if I have a okay, this is going to be, again I'll explain this again. We have a pool of 7 balls and I have 5 drawings. So out of 7 I'm drawing 5, and then I could ask for maybe 0 green. So that's not possible, like I said to you. But I could be asking for 2 greens. That's possible, right? So if I make, so this is out of 5 minus 2. There will be 3. Then that is possible, okay? So 5 minus 2 greens. That is what I want, because this is not possible and that is not possible. And this is N and minus the number of drawings with potential success, which is of 4 in this case, because I could say that 4 are the green ones. So I can have as 4. So I could be subtracting out of that whatever the greens are, in this case 4 and 7 minus 4. So 7 minus 4 would be giving me 3 red. So that is the failure, and that is success over. Now we can have N, that is the total population with N selections. This is not X, okay, this is N. So we can have N selections. Let me just rewrite this N. Now I hope this is just more visible to you. Now this means that our hypergeometric distributions formula is complete, and we can calculate with essentially without replacement concept. The next part is if we want to approximate it to binomial in this case, how do we write that? For mu, that is the mean. Again, you know that mean is actually mu is equal to n into p. So n into, we are not going to get into why we are going to be, considering n into p, because we will be doing that later, but mu is usually the mean is the successes. We want that it should be number of times with the P is the probability of success in this case. So we can have P as a success and Q as failure. So, and sigma in this case would be, but sigma will be different, okay? So sigma square, let's suppose there will be N into P into Q into, now there's a catch in this, okay? In binomial distribution, we just usually finished the formula right there. But when it comes to the hypergeometric distribution, we are going to be, since it is essentially without replacement, so we have to subtract something from the total population. Minus then. Now, when we are talking about subtractions, naturally we can have whatever the trial that we did. So if we have n number of trials, we can subtract that over, and then we can have as the number of times that we can have the sample, okay? So now I give you a number of examples from the book also. I have opened the book and we'll just do a question in this. So now, yeah, where was I? I was talking about, we have n as a sample selections. So we have success. I'm going to be converting that, okay, into the formula right now. q and n minus the number of selections that we made, okay? So number of selections, and by, now we will have n minus, now this is going to be a bit tricky for you because this is now unbiased selection without, this is going to be with replacement, or without, this is going to be without replacement. So we have minus n in this case. Minus n would be the number of selections that we have made. So once you make a selection, you take it out and you can't, put it back. So now this is the total n we have, and we have minus 1 as like the significator. We did that before. If you can just revisit that concept that we have, we can just simply subtract one value to give us the total value of an unbiased probability distribution, and then we can also have sigma as taking the under root of the entire value in this case. Now we will just be reverting back to the book in this case, and allow me just to give you one more concept in this case, and this concept is pertaining to how you're supposed to solve the factorial. So now, when you're solving the factorial, whatever value that comes, if let's say I want to write 5c4 into 7 minus 5 to, now this is n, that was, in this case, our selections was, number of selections was 5. And minus x could be 0 or 1 or 2, so let's just say that it was 2 in this case, right? And this is the possibility of a number of successes. Can we have number of successes as, this could be 2, and this is the possibility of successes as 4. Because we had 4 green, and we had x as 2, because we want to know at least what is the probability that 2 balls out of the selection are green in this case. So now we have total of 7 C, and then the total selections that we did was like 5. Now how are you supposed to open the factorial? Since we have considered usually, cancelling out the common, the way you open this thing is 4 factorial over 2 factorial into 4 minus 2 factorial. Now this is going to be 7 minus 5 would be 2 factorial over, now 5 minus 2 is 3 factorial, so this would be 3 factorial. So this was actually, I'm just going to, for confusions, just remove this confusions 2, and so this is way more actually. So this has to be, there has to be some mistake in this, okay. We have a pool of 7, and out of that we make 5 drawings. Oh yes, there's going to be 4, okay. So now we can have 3, exactly 3, right? So now this is 3, and this is also 3 factorial, right? So for this now, I'm going to be having 3 factorial over 3 factorial, and since this is 3, 2, 3, that means now 3 minus 3 is going to be 0 factorial in this case, right? Now we consider 0 factorial as 1, and this is going to be cancelled by this, so you don't have to really open this, but you have to open this. So for this now, how are you supposed to open this is as 4 over 4 factorial over 2 factorial into 2 factorial. Now I'll just rub this portion so you can just simply see that how you're supposed to do this part. So now if it is 4 into 3 into 2 factorial by 2 into 1 into 2 factorial. So this would be cancelled, 2 by 2 And we can have 2 into 1 and 4 by 3, so this will be cancelled, so usually it's going to be 6. Now that is just the numerator part. Now we will need to also find out the denominator in this case. So we have now 7c5. Let me just open it up separately. We have 7 factorial by 5 factorial over 7 minus 5, which is 2 in this case, so 2 factorial in this case. So now we have 7 into 6 into 5 factorial over 5 factorial into 2 into 1. So now this is 3. And this will be cancelled, so you get 21. So now this would be actually 6 by 21. That will be our answer. So it's going to be 6 by 21. How we are going to be doing other details, let me just go over the book with you people. I'm sorry there's background noise, just kind of ignore this. There are some questions also that I would like you to see. Okay, let me just close this one. Okay guys, I'm going to be hurriedly doing this, and let's just revisit this concept. Okay class, now we are going to be talking about the hypergeometric distribution, where we have probability, like I explained to you, this is RCX n minus R over n over NCN into, this is the probability of success, and this is the probability of failure, where you can see that we have used without replacement concept, and n is the number of population items, where R are successes, that's potential successes we have, and n minus R of these items are actually failures. And if we select n items without replacement, so then we have to subtract R from n and x from small x. Let me just see that this is, they're giving you an example here. So we have 6 stocks, so that means that there's a possibility of having n as the total number of stocks with 6 and 6 values, that is 1, 2, 3, 4, 5, 6 stocks. We have R as the 4 is equal to 4. That is our desired result. That we want basically that there should be 4 stocks that could be potentially available, that could give us potentially positive result. In this case, this is 4, as you can see. Now, that means if 4 is the success, then R is the negative of success. In this case, it's going to be a complement. So n minus R would be 2, which will give us actually the negative return. So negative returns with 2 stocks out of 6 stocks, and 4 with positive result. And if we make 3 selections, so now they have given you x as the probability that x is equal to 2. Now, what is 2 in this case? So this is the probability with the now stocks in population without replacement. So we can not replace them, and x is those selected stocks without replacement that is related to our success, which is the positive result. So at least stocks that are selected out of those 2 would be giving us positive results. So we can have probability as this, and we can have now R would be success 4, out of which we have the probability of x is 2. Now n is the total pool of 6, and 6 minus 4 in this case is 2, and n in this case is if you are randomly selecting 3 stocks. So out of those 3 stocks we have at least 2 that is giving us positive result, and then 4 would be giving us, or sorry, 1 would be giving us a negative result, because n is the total pool of 6 stocks, and this small n is the selection that we make out of the pool of 6 stocks. We make 3 selections, and those 3 selections are represented in the denominator. Then we have our success as 4 positive. Out of those 4, 2 at least should be giving us the positive result. That out of the selection of 3, 2 will be positive or successes. You subtract that to get failure. That means 1 would not be a success in this case. And n in this case 6 minus 2 is going to be your n minus 4 is 2. That is going to be your failure in this case. So how you open the factorial is part of the game. I already told you this part. Then you can just simply 4 over 2 factorial into 4 minus 2 is 2. 2 over 2 minus 1 is 1, and into 1. 6 factorial over 3 factorial into 6 minus 3 factorial is 3 factorial, okay? Then you can just simply find this out. And I've already explained to you that we have n into p, which is the hypergeometric mu. And if it is followed by n having at least 20 times as large, sample selection is not as large as the main pool is. So whatever you select, even if it is without replacement, it's not going to have a too great an impact on the total population value. So now they'll give an example here that say at least 20 times as large. So if your n is way more than the sample size n, it means that it is 20 times as large. So if you take out the sample size, it would still have an impact of having the population values giving you constant successes, or probabilities of success and failure would not be that much impacted. Because if you just want to calculate how many, let's say, gray or white hairs on the head, you just take out 1 hair. What impact will that have on the amount of total hairs on your head? You get what I mean? So now this is going to be sigma square, and then sigma is just under root of this entire value, n minus n and n minus 1, okay? Now let's just look at this, how they are going to be approximating it into binomial distribution. Like I told you, this is n over x into n minus x, which is just the formula for binomial, into p into 1 minus p into n minus x. Now that is very simple. I have explained to you why we are going to be approximating it by binomial distribution, and we can approximate it because the factorial values become very large and n becomes very large. This is just the whole value, the whole point. Let's just go towards this method and application for 5.39, and there are very few questions after that. You can just do all the questions. 5.40, just regarding what I've already told you, just simply put in the values. 5.39, let's just look at that now. I'm going to be solving it right here. They say that x has a hypergeometric distribution with n as 8. Now I'm going to be, first of all, r, what is the value of r is 5. Okay, 5, cx. Now x is actually 0. 5c 0 into n 8 minus 5 over, now this is going to be, now we had if you recall, this is small n, right? So n is a 4 minus x, because this is 0. For our first x, it's going to be 0 again, because of this x. If you just want the general value of the formula, is RCX into n minus r over small n minus x over NCN. That's the formula. So now over n, which is 8, and the small, this is going to be 4. Okay. Now how are you supposed to solve this for x is equal to 0? Like I said, okay, I've written this, but you should already consider the concept I previously gave you. That if your drawings are 4 and your selections are, let's say, 5, okay, successes, and the selections are 4, your drawings, your selections are 4, but your successes are 5, okay, and that means that we can have 8 minus 5 as 3. That is the failure part, okay. So that means if we have 5 as the total positive selections, total positive out of the total selections, the positive results. Okay, so that means that if we draw 4 stalks, but we know that 5 could be positive out of the population of 8, so that means the remaining 3 would be the non-positive ones or the failure ones. So can x be 0? So this is 0 because this is not possible. Because we know that we already have 4 selections and we have 3 failures. So if we have 3 failures and we have 4 drawings, so that means 1 at least in this case would be a success. So we cannot have x equal to 0. So I'm not going to be solving this, right? You already know the answer. This is going to be 0. So let's just move on towards the next portion where we have the probability of x is equal to 1. Now for x equal to 1, you should know that what we could do is, again, write this whole thing as r as 5, and then we have x as 1, so RCX as 1, and then we have 8 as capital N minus 5 over small n is 4 minus 1 over 8, which is n is c, small n is 4. Now, how are you supposed to solve this? In this case, we have, how are you supposed to solve this? I'm going to be rubbing the formula, okay? Or just keeping it a bit inside, because I have very short space, small spaces, small space. Now, 5 factorial in this case would be just, this is 1 factorial into 4 factorial. Okay, because now we have 5 minus 1. Now this is 3. So I'm going to write 3 factorial over, we have, what's this? Again 3 factorial. And we have, now what else do we have? Since this was 1 factorial, this is 3 factorial, and this is 3 factorial, and then it's going to be 3 minus 3. Right? So this was actually 3 and 3. So it's going to be 0 factorial, right? That is going to be just 1. By, then we have 8 factorial over 4. So it's going to be 4 factorial into 4 factorial in this case. So now, this, when you open this thing, it's going to be something like 8, 7, 6, 5, 4, 3, 2, 1 over 4, 3, 2, 1, which will be cancelled. And this will be again 4, 3, 2, 1. Now, this would be cancelled by this, and this is going to be 2. So it's going to be 14 into 5. So you can just simply calculate this 14 into 5. 5s are 27. Okay, so it's going to be 70. Okay, so now our denominator is going to be 70 over. Now, what do we multiply with each other? This is 5 by 4. So this is going to be just 5 into, this is just 1. Okay, so it's going to be 5 by 70 something, because this would be cancelled by this. And since this is 5 into 4 factorial, basically this is 4 factorial, so just cancel and you get 5 by 70. And let's just divide this and find out what the value comes to. So we can have 5 by 70 comes to about 0.07142. 0.07142. Now let's just move on to the next part where we have x equal to 2 and you can solve the remaining one. And for the last one, you should know that this will be actually probability of x is greater than 1 is 1 minus probability of x equal to 1. So I'm going to be, whatever probability that you had, 1 minus this probability will give you actually probability of x greater than 1, right? So less than, since it is greater than 1, so this will, had it been greater than or equal to 1, then we would have had probability of x, less than, or 1 minus probability of x is less than 1 or equal to 0. But now since it is just greater than 1, so we can just have probability of x equal to 1 subtracted from it, and you can just have the remaining probability. And for x equal to 2, just one more example how to solve this. Now, as you know, instead of x having 1, now we have as 2, and 8 minus 5 will remain constant because we have, this is r, and this is the number of successes that we already have, and that remains constant irrespective of what is the potential, of what is the positive result that we want to find the probability for. And or the probability of the desired outcome that we want is going to change here. So that in this case will be 4 minus 2. And now this is nc small n, and this will also remain constant. That won't change. So now we can have this as 70. Because see, this is just the same. What we need to find out is this thing, right? So we have 5c2, which is actually 5 factorial over 3 factorial into 2 factorial, okay? And then we have 3 factorial over 2 factorial into 2 factorial, 2 factorial into, so now this is actually 3c2, so this is going to be 1 factorial, okay? Yeah. So this is 3c2, and this is actually 3 by 2 into 3 minus 2 factorial, right? So it's going to be 1 factorial, and then we can have this as this. So now let's just solve. This is actually, if I open this thing, what will it be? Well, 5 into 4 into 3 factorial over 3 factorial gets cancelled. Now this is 2 factorial gets cancelled with 4. Because 2 factorial is equal to 2, so now we have, where essentially this is 2 and we have 10 as the answer for this part. Now this 3 is actually 3 into 2 factorial would actually be 3. So it's going to be equal to 3, and this is going to be 30 by 70. Now how much does that become? So we have 30 by 70 as 0.428. This is going to be equal to 0.428, okay? Similarly, you can just have mu as n into p. N is the, now if I were to write the binomial distribution for with n is 10 hypergeometric distribution, but if you just write out the success is r, for just finding out simply, you can have this probability as of success is r as 4 by the total of 10, which is 0.4, and failure in this case would be 1 minus 0.4 is 0.6, right? So you just simply write this down as 0.6, or 1 minus is also equal to 1 minus r over n. Okay, so this is going to be 0.6. And so now we can have nc3, but if you want to find out with the, just to find out mu, if you want to find with the binomial distribution, if you just to approximate it according to this. But you can also find out with the formula with ncn. And you just repeat the entire thing, but hi class. So we are going to be talking about the question which is 5.39, and suppose that x has a hypergeometric distribution. So now we are going to be solving this question with n is equal to 8. This is 5.39. Okay, this is hypergeometric distribution. N is equal to 8 and r is equal to 5. So we have r is equal to 5, and I've already told you that n and r basically are linked in a way that n is a whole pool and r is basically the selection with the successes in mind, the potential successes that we're going to be having, and n is equal to 4. So small n is equal to 4, and you have to find probability of x is equal to 0. So part A is probability of x is equal to 0. Now, like I already explained to you that if we have the pool of 8 and we have successes as 4, that means we have failures as 3. So for this purpose, now if we are to draw 4, that means that x cannot be 0. So this first probability is going to be 0. Now I'm going to be writing down the formula for this, which is actually, I'm just going to be writing it in this portion, that we have r x and n minus r for failure, that's going to be for success, and small n minus x for the failure selection, and then we have n c n. Now to solve this factorial, remember that I gave you this explanation that we are having r factorial over x factorial into r minus x factorial. Okay. And in this way, we can be solving the other ones. So now let's just go for part B, which says that x is equal to 1. So now we have probability of x is equal to 1. Now I'm going to be solving this particular thing. So we already have r as 5 and x as 1. Okay. Now the pool is 8. So we have 8 minus 5, which is actually 3. So I'm going to be writing the explanation solved value as here. And now we have small n as 4 and minus 1. So this is also going to be 3 divided by, now we have n as 8 and we have small n as 4. Now to solve this factorial, I have to, delete this part. Okay, so in order to solve the factorial now, we have 5 factorial over 1 factorial, okay, into 5 minus 1 is actually 4 factorial, into, now I'm going to put a small cross so that you can differentiate it. This is actually for multiplication. Then we have 3 factorial over, since we're coming from here, this step, over, then we have 3 factorial into 0 factorial for 3 minus 3. With the same formula that per factorial we're going to be using the same formula, over. Okay, so now again we have, alright, so this is actually, alright, I think this was 3 over 3 factorial into 0, yeah, this was correct. Now we have over 8 by 4, so this is going to be 8 factorial over, so we have 4 factorial into 8 minus 4, which is 4 factorial. Okay. Now we are going to be solving first the numerator, and then we are going to be going for the denominator. If you can see, if I open this factorial, because I cannot, have too many steps here because there's this limited space, so I'm going to be solving this part right here. So you can just see, I'm just going to be breaking this with 5 into 4 factorial, because it's going to be 5 into 4, 3, 2, 1. So 4 factorial and 4 factorial are going to get cancelled, and this just comes to about 5. And in this, you know that 0 factorial is 1, and I've already explained that why 0 factorial is 1. Just go back to one of my lectures and you'll just, recall this part. But basically, you cannot multiply anything with 0 because it comes down to 0, and the minimum value that we have is 1, which will be the value with which 0 can multiply itself to get again 0. So 0 factorial is just, you can just go back, and you cannot have a negative value also for factorial, okay? So now 3 factorial will be cancelled by 3, it's just 1, okay? And then divided by, so this is just 5 over. Now we have 8 factorial, so I'm going to be opening this entire thing as 8, 7, 6, 5, 4, 3, 2, 1. Now do remember this, I don't have to open this 4, 3, 2, 1 because this is just 4 factorial, okay? So I'm just going to be rewriting it as 4 factorial and I'm going to be dividing it with the 4 factorial and 4. So I'm going to be just opening this, okay? 4, 3, 2, 1. And the other I'm going to be writing as 4 factorial. And this 4 factorial with 4 factorial gets cancelled. And this, now you can see 6. And this is 2. So now you can just multiply this with, so this is 14 into 5. 5 4s are 20. So this is actually 70. Okay, so now we have, this is actually 70 and this is 5. So this actually comes to about, this is, okay, I'm just going to rewrite this as 5 by 70. And you can just find out what is the decimal value of this with the help of the calculator. And also remember that you can also find online the value of factorial. And it's also given in your calculators. And you just simply press the option for that. But you have to open it as per this formula. And I've already told you that since hypergeometric distribution can be approximated to the binomial distribution if n becomes very large. And the reason I told you was because since you can consider, for example, the value of dust particles, I say, on my mobile phone right now. Okay. So now for these, I can, even if I remove one speck, that will not affect the probability of occurrence of successes for various other specks that are there. Therefore, it will not impact the result of the total pool of successes or failures. Therefore, we say that this is even without replacement procedure, you cannot impact, therefore, it does not depend even if you replace the drawing, because it will not overall impact the result of the outcome. Therefore, we can say that we can approximate it to binomial distribution, because for binomial distribution, you have the with replacement result. So it just comes to that. Now, we just find this out. 5 by 70 comes to about 0.07142. So this is actually 0.07142. Okay. Now I'm going to be going for probability of x is equal to 2. And I'm just going to be making changes here so that you can just simply understand. This will be 2, this will be 2, and 2. Now just notice that this is since 2, and we have NCN will remain constant. Okay, so you divide it by 70, that will not change, this will not change. Okay, so now I'm just going to be solving this value, Okay, so now this is actually, let me just rub this off. Okay, this was 0.07142. Let me just write it. And this, we are going to be changing it to, since we have already 4, this was 70. And now I solve for this. So 5 factorial over 2 factorial into 3 factorial, which is actually 5 minus 2. And then we have a 3 factorial over, then we have 2 factorial. 3 minus 2 is actually 1 factorial. Remember that I said we have 0 factorial as 1. So now we have 1 factorial is just 1 again. Now, but for this, if I open it as 5, 4, now 3 factorial I'm going to write instead of the 4 factorial. Now I have 3 factorial, and I'm going to be cancelling it with this 3 factorial. Now we have 2 here as 2 into 1 is just 2. So now we get 10. So I'm going to be writing 10 into something over 70. Now this is 3 factorial over 2. So now I have 3 into 2 factorial over 2 factorial into 1. So 1 will remain 1. So I have just 3 value left. This is 30 by 70. Let me just find out what the value comes to. So this is 0.42857. So this is going to point 4, 2, 8, 5, and 7. Okay. Now we have probability of, okay, now if you look at part H, I said that probability of x is greater than 1. Probability of x is greater than 1 would actually be 1 minus probability of x equal to 1, because see, this is greater than 1, so it can be probability of x equal to 0 and 1, but since 0 is 0 in this case, so you're not going to be adding that up. We'll just be having probability of x equal to 1, just making use of the complement process that we already done in the conditional probability, okay? So just go and visit that lecture if you don't understand what is complement, and you can also do section 6 of this book, which is actually Stefan Weiner and Stephen Kostinoble, and this is Finite Mathematics, 7th edition. Okay, so when you have 1 minus probability of x equal to 1, we have already done this here. Probability of x is, so 1 minus 0.42. So I'm going to be writing it as 1 minus 0.42857. Okay. Next, okay, so probability of x is equal to 3. Then you can also do probability of x equal to 4. And let me just do probability of x equal to 3, then you can just calculate the other parts. Again, you should be knowing how to solve this factorial, which is of main importance, because if you just write and you give the wrong answer, that is also not going to be giving you or contributing towards the marks. Now, again, if I keep raising the number, so if I have probability of x equal to 3, in this case, will be, I'm just going to be rewriting this part. This is actually 5c3, because it is just RCX, it's just 5, and C3 into 8 minus 5, but that remains the same because we have R as constant, and 4 minus 3 over, and then we have 8C4, that won't change. Now 5 factorial over 3 factorial into 5 minus 3 is 2 factorial, and then it's going to be 3 factorial over 4 minus 3 is actually 1 factorial. So this was 3 over 2, 1, 3 combination, 1. So 1 factorial, and this was 3C1 actually. So that means that 3 over 1 into 3 minus 1 is actually 2 factorial, right? And then over 70, we have the final value as, I'm going to be opening it here just for explanation. I just wrote the main value, then I'm just going to be expanding it. 5 into 4 into 3 factorial. So now this 3 factorial will getting cancelled by this, and 2 will be cancelled by this. You have 10, and this is actually 3. Again, you have 2 into 1. Okay, so this is 2 into 1, and then we have 1 factorial. So this is just going to be again 3 into 2 factorial. Okay, so now you just have 2 cancelled, so you just have 3 here. Again, you have 30 over 70. Let me just revise this. I hope that there's no mistake in this. So we have 8C4, and we have 5C3, and we have 8 minus 5 and 4 minus 3. Now we have 5 into 4 into 3, and then 3, 5 minus 3 is 2 factorial, and then we get it cancelled, and then you have 10 basically, and this 3 gets cancelled by this. Then we have the 3 factorial over 1 factorial to 2 factorial. So just the same answer, perhaps just 0.42. What was, I didn't write the answer, 0.42857, 0.42857. This is just the same value that we had for probability of x is equal to 3, okay? So you have to keep changing and differentiating the values, because once it gets constant, if you keep increasing the value, the probability of x will keep reducing as well, and it cannot exceed 1 and it cannot be negative, okay? So just calculate all the remaining parts in this. Let me just discuss with you why we are going to be talking in terms of binomial distribution here. So if you have mu as the mean, and in binomial distribution, I said that mu is actually NP. And so you have sigma as npq under root, right? So now we have n as the same, and p, I said this is going to be r by n, so because this was success probability, and that failure would actually be 1 minus r by, so we have 1 minus r by n, okay? Just this part, subtracting it from 1, you get q, and then now we have, like I said, n minus n, because this is without replacement, so you are going to be selecting something, and from the entire pool, whatever that you have selected, you're gonna not count it because you're not going to put it back. So if I have a bag of balls, so I take out 3 balls or 4 balls in this case, I'm not going to be putting back those balls. So I have to subtract that selection, and since n minus 1, because I need to be unbiased in my selection, okay? So we have this entire for sigma, and then you can just simply put these values, and then you can just have, this is actually variance. So now you can just have it in under root, and you can just have the sigma, and the same, this concept has been tested in 5.4. They are asking you to write the probability distribution just in the way you write the probability distribution is just by probability of x equal to 0, 1, 2, 3, up to, since you have 4 selections or 3 selections for 5.4, so just as x equal to 0, 1, 2, 3, because you can't really go more than that. So just be very careful about this. And now they are asking you to find out the mu in this case. So mu is actually for 5.4. So this is actually n, where n is 3, and p is basically dependent on r, which is 4 by 10 in this case. So 4 by 10, which is actually 0.4, okay? So just simply 0.4. Now this is mu. So just find out the value. 3 into 0.4, and you get 1.2. This is the mean. Now if I want to find out sigma square, in this case it's going to be npq, and it's very simple, it's 3 into, because I'm going to be finding out with the help of this formula, so this is 1 minus r by n is going to be 1 minus 0.4, which is actually 0.6 into 0.6, okay? And then n minus n over n minus 1. So now n in this case is 10, okay? So 10 minus small n, which is 10 minus 3, okay? So we have 7, okay? So 7 by 9, because n minus 1 is, so we have 10 as n, capital N is 10. So 10 minus 1 would be actually 9, 7 by 9. So now you have 0.4 into 0.6 into 3, and you have 0.72, and then 7 by 9. You have 0.56, okay? So you can do other questions. If you have any issues, you can just simply write them down, state them in the comment section, and I'm going to be, I would be happy to answer to you. There's another concept that I wanted to discuss the other day, and this when we're talking about the coefficient of correlation. If you remember chapter 3, this is also in one of my lectures. You can just simply search with the title of covariance correlation. We already know that we did SXY and we did SX. So it's actually summation x into x minus x bar whole square over n, and it's going to be n minus 1 if we have sample standard deviation for x. So y also, and then we can have for summation x minus x bar into y minus y bar. Okay, it's also going to be summation over, then we already have Sx into Sy. And this is how you're supposed to calculate, but this was also for correlation coefficient. There's another formula for you to find out correlation coefficient. I wanted to discuss that with you. You can simply even search it in Google if you want. And this is actually n into summation xy minus, because it also depends upon what kind of question you're getting. If you're getting the values of x and y's, and x could be anything, for instance, the number of miles that you're traveling from one city to another, and y could be per city, city 1, 2, 3, so on and so forth. So you have minus summation x into summation y over, then you can have this and summation x square minus summation x whole square under root into, then again you're going to be having another under root as n summation y square minus summation y whole square. So you get R, which is actually the explanation of variance with regards to one variable to the other. So you correlate the variables and you see that the relationship between the two exist. So I can see that maybe the mileage from one city to another is actually impacted by the city that you're traveling to because of the fuel prices that would vary from city to city. So from, if you're traveling, let's suppose from Pindi to Islamabad, or you're talking from, from one state to another if you're living in, let's say, United States. So it could be, or in Canada, you're going from Ottawa to, let's say, Toronto. So for that, you can say that from Toronto, then you travel to Windsor. So the fuel cost could, vary. So that depends upon the fuel prices. If they are not the same, they're variable. So in this case, this would be explaining the variability with the help of the relationship that exists from distance to distance and place to place. But now there's another thing which is known as R squared, which is coefficient of determination, okay? So coefficient of determination is basically, for instance, if R comes to about 0.97, then if you square this value, 0.97 squared, and let me just find out how much does that become. This would actually reduce the value of the coefficient of correlation. And why we do it? Because we want to be conservative about our reporting. Why we need to be conservative is because we don't want to be too overly confident that these two variables are together interrelated. We want that they should be, explaining a part with when we are actually sure of this is the minimum that these are reporting, these variables are reporting. It means that if I say into 0.97, it comes to about 0.9409, which is actually 0.9409. That means it is reduced from 0.97. So I'm determining, so this is coefficient of determination, that I'm determining that the remaining 0.06 something or 0.5 something, 0.6. So just if you want exact values, it's going to be 1 minus 0.94. 0.409 comes to 0.0591. So I want to be sure that this 5% is an error. This is error which is reportable or attributable to some other factor which is not explained by these two variables. So this error is actually the residual value that you get at the end of solving the simple linear regression problems. So we do this in least squares, and when we talk about Minitab and other softwares, I would actually prefer if you use Excel first, and then we can discuss Minitab maybe later on maybe some other point, at some other point, or on some other occasion. At this level, I think that if you just do these formulas and these concepts should be enough for you.
मैं आज पता है हम इसके महसूस हुए कि आज मैं पहली दफा पढ़ रहा हूँ क्लास में डालने फिर बाद में ये कहेगा नहीं हुआ दूसरा नहीं हो गया ये हो गया वो हो गया इसलिए इधर उधर करेंगे ये छुट्टी नहीं ठीक है सर जाते तो गाड़ी वाला काफी तेज